Okay, so we are still on combustion. What we're going to do now is we're going to look at the energy in combustion. So this is in form of enthalpy. So to start with, we're just going to have a little revision from CHM. So we're going to start with enthalpy of formation. So the enthalpy of formation is basically the amount of energy that is needed to break up molecules. To break up a molecule, into single elements. Bear in mind that for pure elements, first we're going to the reference temperature, which is, okay, we'll just T0 is equal to 25 degrees Celsius, which is room temperature. Then the reference pressure will be equal to a normal 100 kilopascal. So the enthalpy of formation, the standard enthalpy of formation is the enthalpy of formation at the reference temperature and pressure. For pure elements, so these include pure elements and pure molecules, so these include O2, C, H2, He. The enthalpy of formation, standard enthalpy of formation, is equal to 0. Then for molecules, each molecule has got a different, each molecular compound has got a different enthalpy of formation. So what we're going to see is, let's try with carbon. If we do carbon plus oxygen, we get CO2. So what happens here is we have carbon coming in and oxygen coming in at 25 degrees Celsius, and this is also at T0, and it comes out as CO2 at 25 degrees Celsius. We're going to have an amount of heat which will be lost. Okay, so for us to get the enthalpy of formation, the formula is QCV plus so this is just saying that these are the initial reactants, or the initial elements or compounds that are available. Then these are the ones at the end. So these are the products, and these are the reactants, and these are the products. This is the number of moles, this is the number of moles. So like I said, for carbon it's 0, for oxygen it's 0, but for CO2, from your table 810, CO2 enthalpy of formation, standard enthalpy of formation is equal to, for CO2, standard enthalpy of formation is equal to negative 393522 kilojoules per kilo mole. Okay, so our QCV here means will be equal to NEHE minus NiHi, which will be equal to so this stands for the enthalpy of formation. This is also for the enthalpy of formation. Okay, so which will be equal to 0. Sorry, this is not 0, this is 0. So this one is for the carbon dioxide, which will be negative 393,522. Then Ne is 1 minus this side, it will be 0, which is equal to negative 393,522 kilojoules per kilo mole, which is this heat which is given out here. Okay, then after that, what we're going to look at is to find the enthalpy of formation at. So we are done with this. So now we're going to do the enthalpy of formation at a different temperature and pressure. Okay, so for the enthalpy of formation at a different temperature and pressure, what we do is we get the enthalpy, standard enthalpy of formation, plus the change in enthalpy from T0, P0 to T actual and P actual. This is just finding the enthalpy, the change in enthalpy from the standard condition to the actual condition. So let's say if, for example, we had a pure gas, if it's looking for enthalpy of formation of, an ideal gas, it will be equal to HF0 plus Cp times change in T, which is equal to HF0 Cp T0 minus T actual. Okay, so now, this is the enthalpy of formation for just one substance or one molecule, not for the whole reaction. So QCV is the enthalpy of the reaction. Okay, so this enthalpy, we're now going to look at finding the enthalpy of a reaction which is not at the reference temperature and pressure. So QCV plus enthalpy of formation standard plus change of enthalpy. This is for the reactants. The R is for the reactants, is equal to the work that is produced. If there is no work that is produced, please just leave it as 0. Just cancel it out and leave it as 0, plus the summation of the products plus change in HE. Please bear in mind that the reason why this it's been multiplied by the moles is because the enthalpy of formation is usually given in kilojoules per kilo mole. Okay, so now we're going to look at an example. So let's say we have C3, H8 and air coming in at 25, or coming at the reference temperature and pressure, then coming out as carbon dioxide and water at the reference pressure but temperature of 1200 Kelvin. Okay, so what we're going to do here is we're going to first balance the equation. Okay, let me just first put it in diagram form so that it can be more visible and be clear to understand. So what we have here is C3, H8 coming in, and then we have air, which is O2 and N2. Okay, So, and we have the reactants here, which are CO2 and H2O. So these are at T0, this is at P0, this is the control volume, and then this is at T is equal to 1200 Kelvin. So we have QCV, which is our enthalpy of reaction. So what we're going to do first is we're going to write the equation C3H8 plus O2 plus 3.76 N2. This is an equation of combustion. So we have CO2 plus H2O. Okay, so we first balance it out. How many carbons? 3 carbons here. How many hydrogens? 4 hydrogen. Sorry, this is 100%. Or let me just, this is theoretical air. Okay, so 3 and 4, so which means how many oxygens do we have here? We've got, I'm just gonna put the N2, I've got the N2 here. We've got 4 oxygens here, and then we've got 6, which is 10. So to get 10 oxygens here, we have to put a 5 here. So which means even the hydrogen has to be multiplied by the 5. Which is equal to 18.8. Sorry, there's no space here, but it's supposed to be 18.8. Okay, so after we do that, now what we're supposed to do is we get our equation, this equation here. So QCV plus R, which are the reactants, Ni HF0 plus change in H is equal to WCV plus the product Ne HF0 plus change in H E. Okay, so we're going to start first by finding the HF0, which is in your table A10. So in your table A10, this we're going to find for both the reactants and the products. So in your table A10, HF0 for C3H8 is equal to negative 103,900 kilojoules per kilo mole. Okay, then the HF0 for O2 and N2 are both 0. This is because, like I said, these are pure molecules or pure elements. Both of them are 0. Okay, then we go to the enthalpy of formation of water. The standard enthalpy of formation of water is equal to negative 285,830 kilojoules per kilo mole. Then the standard enthalpy of formation of CO2 is equal to 393522 kilojoules per kilo mole. Okay, then what we're going to please bear in mind that this enthalpy of formation of water, please take care when you're looking at water. This at reference temperature and pressure, water is in liquid. So you have for liquid and you have for gas phase. So for water you've got liquid phase and gas phase. So you choose the one for liquid phase since it's in liquid. So now I'm going to check the values, the change in enthalpies. So for C3H8, it remains at the same temperature. It's at reference temperature and pressure. So the change in enthalpy is equal to 0. Then for air, first of all, these are pure gases, so which means the change in enthalpy, the enthalpy of formation is 0, and even the change in enthalpy is still be equal to 0 since it's at the same temperature. Okay, then what we're now going to have is the CO2. For the CO2, like we said, for instances, like we discussed in gas mixtures, when we have gas mixtures, please treat them as pure gases. So what we're going to do is, for CO2, for us to get the change in enthalpy, we're going to do Cp times change in temperature, which is equal to, with your Cp value from your handout is 0.847 times the change in temperature, which is 298 minus 1200, which is equal to, so this is 0.847 times 298 minus 1200, okay, which is 764 kilojoules per kg. Please pay attention to the units, so we need to convert this to mole. So for us to convert this to the mole, we multiply by the molecular mass, which will be equal to -764 times, so our molecular mass for oxygen will be 16 plus 12, which is 28, which is equal to -21392. Then we're going to find the change in enthalpy of water, the change in enthalpy of the H2O. To find the change in enthalpy of the H2O, we're also going to assume it turns into an ideal gas, but we can also use the tables to be more accurate, but we're going to use the Cp value for water just so that we can be quicker.